this webinar, I think before I start, like I can give a brief introduction about like who we are. So my name is Pravin, and I'm joined with along with James, my teammate here from Ad Composites. We are the I think one of the uh, biggest now AFP providers, system providers out there in Europe and USA, I believe. Um, yeah, and I think the idea of the webinar came about by to spread the knowledge that we have gained by running the system for now uh, 2 to 3 years, and mostly uh, we have used certain different types of heating systems. So in this webinar, that's what we'll focus on. Yeah, so I'll get on to it. What we will try to cover in this webinar. Um, for different material, what process parameters you would need, and how to arrive for your given material to those particular process parameters is what we'll talk about. Troubleshooting and addressing the common issues that we have seen while running the system. We'll talk about those and how to go and overcome those, and then how to really optimize the process with the given set of resources, be the different heating system or different AFP systems, and what could be the best practices for achieving a good quality thermoplastic laminate. What we will not cover in this webinar is the planning and layup strategies that are specific to thermoplastics, um, mold design that is good for doing thermoplastics, and different heating technologies like laser or flash lamp or hot gas torch. So we'll mostly focus on the aspects that are mentioned earlier. Yeah. So the very first aspect, and that is, I think, the most critical as well, is the temperature requirements. So there is a great selection of material out there that is available in terms of unidirectional thermoplastic tapes. This is just a common list that I grabbed from the internet that are most commonly available unidirectional tapes. And what you can see in front of them is what we recommend as a processing temperature, and this is something we have done like a lot of trials with. But a good rule of thumb is like about 30 degrees Celsius above the melting point temperature. So for PP, PA6 running along with glass fiber, carbon fiber, there is definitely different requirements. There is no exact number, and we'll talk about like why there is no exact number. But this is where the first thing starts, like depending on the material that you have chosen for your application, knowing like this will be the processing temperature help you decide a lot. The next bit is actually that would come is the heating of the bed. That is coming from, as most of you might have at some point of time used a common 3D printer uh, with the heated bed and non-heated bed, and you would see this warping happening. So it is generally recommended to have a heated bed while running thermoplastics. And once again, we have done a lot of trials with different materials, and we see that it's usually around the TG of the material or the room temperature is the best bed temperature. Um, one of the most requirements. Do you have something, James?
I'm going to say we omitted LMP material on this, which is more and more popular in the research areas. It has similar properties to PEEK, but the melting temperature is around 30 degrees Celsius lower, which may not sound like a lot, but at this temperature range, it actually makes a pretty significant difference in the processability of it. So just wanted to throw that in there as well.
Yeah, thanks. I think that's definitely a very recent development, and I think it's a very valuable input that should be here. So yeah, but I think coming back to the heated bed temperature, it's mostly focused or like kind of derived from the TG of the given material. And this is kind of also true based on literature, that like you would want to have the base temperature to be at least around the glass transition temperature. Yeah. Then I would say we go into the actual heating part of it. So we know now what is the temperature requirement, and we know like what temperature should our bed be, or the mold or the tooling be at to do the thermoplastic placement. Um, then the next thing is choosing the heat source. So assuming you have a given heat source available with you with your AFP system, could be laser. In this example, what is shown in the screen is it's actually a flash lamp. Um, and this is quite compact flash lamp, so it's like allows you to do quite complex geometries. So it's very critical to have a heating system that is compact and not intruding in the, if you have a complex geometry, it won't collide or something like that. And the ability of the heat source to get really close to the point, close to the nip point, is very very crucial. It really helps the heat distribution to be very close to where the actual bonding or melting is happening. Yeah, as you can see, also the second bit that I'm written down is the angle of the heat source. That actually creates the main how the heat will be emitted from the heat source and will be impinged, or the direction of it getting absorbed by the incoming tape and the substrate. It's very critical to get those very well aligned. If the heat source is, let's say, kept far, what ends up happening is because there is a bit of a curvature at the incoming tape point, uh, the heat that is hitting the incoming tape is not equally distributed. So you're kind of getting uneven heat, but then you might be still able to get okay temperature. And substrate is also kind of is at a certain angle of the incoming heat. So having a heat source that is able to angled in right way is really really helpful. And then focusing of the energy, yeah, I think that is something I will talk about a bit more as well with the incoming fiber angle. But the incoming, so the what you are looking for is,
Sorry. Can I interrupt? Someone raised their hand, but if you have a question, you can go into the bottom right, the activities button, and there's the Q&A section. So you can ask a question in there, and then we will answer it on the webinar. Thanks.
yeah, thanks. So just focusing of the energy, because as you can see, the exposed area in the to the incoming tape to the substrate is not usually equal. You have much more substrate usually exposed compared to the incoming tape, and this would vary depending on the system you're working with. So what you're looking for is getting the energy to the right place. And sometimes that would involve like different strategies that you can employ to get the exposure higher for the incoming tape. But you don't want it to get too high, because then you might end up burning the incoming tape as well. So there is a balance. So really need to have a heat source that is really well designed for approaching this. The second bit that is more focused on to is the incoming material. So the incoming fiber angle, as you can see, in this case with the FPXS, I think it is about 60 degree from the substrate, but it can be changed depending on the geometry. So by changing this orientation of the tool in a way that it is rotated about the vertical axis, it's able to increase the exposure length, and you're able to have much more exposure available for the tape from the heat source. So this is one of the strategies that is really crucial, and it allows you also to play with the heat source distance from the substrate. So having the incoming tape angle changeable, it also is really helpful. And then we talk about the heat source intensity. Um, so heat source intensity is a function of basically the speed that you would want to have. There is one very decisive approach by which you can arrive for a given material what heat source intensity should be, but for a given speed. There's a design of experiment I talk later in the presentation about. So we'll come to that. Yeah. And then heating uniformity. And this basically comes from the type of heat source you have available, but still, the more control you have, because not all the material absorb the energy the same way. So if you have more parameters to play with, where you can change how the heat is given to the material, be the incoming tape or the substrate. uh, so with in case of the flash lamp provided by Heraeus, has the you can have the pulse width, the intensity of each pulse, and the frequency of those pulses. And you can, this is the profile that you are like, you can optimize with and try to achieve a very good uh, heating uniformity for the given material and the substrate. So this is kind of the profile. Then the other way is also from some of the recent developments. There is a Vexel system that uses multiple small lasers to impinge different let's say small lasers at different locations of incoming tape and substrate, and you're able to achieve a better heat distribution using something like that. There is always a, yeah, compromise, but this is something put together all of this. So starting with the knowing what material we have, what substrate temperature we have, and then choosing, like having a heating system and changing the parameters is what all gets you to the temperature of the material that you would have at the end, that is at the nib point. um, the next bit is, as I said.
Sorry to interrupt that question. It was, will we be provided with a recording of the webinar? And the answer is yes. Everyone will be sent a recording of the webinar on the email address that they registered with.
Awesome. Yeah, so let's dive into the design of experiment that you should run with your material, with your system, that would help you arrive at the best, I would say, parameters and planning strategies and things like that. So, so for the design of experiment, you would focus on creating nothing but just one single strip of tape that is placed repeatedly over and over again. And you would want to have all the different parameters. That is, you have a certain intensity of power, heat profile, and the speed that you start with, usually the lower end of it. And then you would want to change it successively to arrive at a better version that is uh, more suitable and allowing you to see, oh, there is, now I see some bonding happening. And then you would do that at different speeds. um, Always remember, the speed is not linearly changing with the given power. So the other way, sorry. So the power intensity and the speed, they are not linearly correlated. So you should definitely, if you're going to change the speed of the layup that you're running at, you should definitely do the DOE around few different speeds and see okay, what power intensity it works better with, and then see, okay, um, you choose that profile for that certain speed. And the other parameters that definitely help is pressure. So the more you consolidate or apply pressure, or the longer duration you do that, it really helps with the diffusion and like achieving better interlayer bonding. Uh, and there is, I talk about this later at the presentation as well, like what key property does it affect. um, and then the tension is very critical, because the tape start to melt and curl, so you need to apply uh, relatively higher tension compared to thermosets for doing thermoplastic layups. But this is one of the parameters that you can very easily arrive at doing your DOE. Feed and cut, and this is more to do with the tabs, you know. So you usually would want don't want to have the uh, let's say non layup areas to be less exposed. So usually the layups have thermoplastic layups have been done with the starting of a tab. So they would feed some extra material and then they would start the layup. That way the compaction roller is less exposed. But with today's software and controls, you can actually really arrive at the parameter where you can have the uh, beginning of the tape coming at the right time, start of the heating, and then same thing with the cut, and exactly when the heat turns off. With AdPod, what we are able to do is actually go into the millisecond level control. So before or after the approach, 2000 milliseconds, and I know I have to turn on my heating, so the initial point of the tapes get heated. So this is very critical for achieving almost a tabless thermoplastic layup. So this way you don't waste the tab area, and it also allows you to do selective reinforcement in the middle of the layup. So this stage you can really figure it out, like are you really getting the beginning and the ending of the pass really well exposed. And you just have to make sure that you're not burning the roller. So that's the other side that you want to balance here. Other than getting to all these key parameters, what you also end up getting is the consolidated thickness. So let's say if you did 10 layers, you can measure the thickness and know what is the consolidated thickness going to be. And this is the input for you for doing for the planning. Then tool tilt and exposure. So you start usually with, as I said, lower side of the things. You can change the tool tilt if you're not able to get to the speed that you desire, enough power. So now you know you need to overexpose with the heat signal, so heat input. So that's what you really want to get here. And this once again will be the input for the simulation and sensor positioning. So you definitely want to know what temperature your material is reaching at and it's not degrading. So at DOE, you should definitely get uh, the sense of this. And with that path, you usually are also able to trace it back. There's soon the capability to even like have it recorded for the entire layup. So then you are able to also go back in the history. So this is something very critical for you to know that you have not degraded your thermoplastic layup. Yeah. Going to the heating element, I think, and this is goes into the choice that you have and how many parameters can you play with. So usually with the flash lamp, there is you can play with the, as I said, the intensity of each pulse width, and the frequency of those pulse. With lasers, I think there's a certain wavelength, and then there is the guide optics that is focusing the intensity, and that can be distributed on different uh, widths. So depending on the optics, and certainly the power. Yeah, and I believe there is also the how far can you have those and how much loss, or how would you say underexposed area you would get. So you would want to have them close, so then they are only focusing in the right area in the right way. Yeah. um but yeah, I think assuming now you have run you have understood initially your heating requirements, and you know what are the critical parameters, and now you have run your first design of experiment, that is just running the first strip and getting all the key parameters out. Now you would get ready for doing the final layup. And what you really want to pay attention is, now you get into the planning zone. So you have the planning part, which is I don't think so people pay enough attention to doing the planning. But let's say, talking about the first layer for thermoplastic, it's a very classical example that you won't be able to stick it to a metal base right away. So the common practice is to use a thermoplastic release film to place it, but the thermoplastic won't stick to the release film. So how to get it to stick? So for the first layer, usually there are two strategies that I would say works quite okay. One of them is basically, for the first layer, you always want it to do slightly bigger, so you can apply some sort of tape at the edges and without disturbing the actual layup area section. And then you would want to have some sort of approach to bond the first point or staple the first point and the end point. So that can be achieved either by putting just the same thermoplastic strip, a UD tape, perpendicular to the direction of the layup at the beginning, at the end point, and you just put like a double-sided tape under it or something like that, and then you start. Because now at the beginning point there is the thermoplastic strip, and at the end point you're able to get some sort of starting and ending, and it start to hold well. If the material is very high temperature, so if you're talking in the peak zone, you will see warping quite heavily. So either you get like a good a good tape, or the other way is to first layer to do just at no temperature at all, so you don't turn on the heat at all. You just put some sort of thermoplastic glue that can help you stick the first layer, and then you start to do the second layer. There is still the challenge of warping, so you would still have to tape the edges. Yeah, so I think that is the strategy for the getting the first layer to be good. Yeah, and all the parameters that now we got, from the tool tilt to minimum cut length to ex- not having the tabs, we put in here, and really make sure for the planning you input those values. Then the timings with the similar input that we got, and then check certainly for the collision at the tool level, more level, and then also see how the cabling is going to be moving around, and if you have it correctly um, loosened enough, and then yeah, so it's slightly difficult to see with the collision simulation, but you can get an idea with the motion range of the robot that the cabling that you have available at your facility is appropriate or not. Yeah, so I think we already talked about the first layer quite a lot, and definitely heat and if possible, otherwise there is going to be some warping, and definitely put some tapes on the boundary. Yeah, I think now we are getting to very close to running uh, the layer. Now we come to the cooling and the pressure side. So you always want to make sure that you have some sort of cooling towards the end of the compaction, because it will get overexposed to the heat, and you want to run it consistently. So you want to have cool rollers, and at what temperatures those roller can hold up. And yeah, and certainly the pressure. Sometimes the pressure can be like the higher the pressure the better, but there is like a diminishing return after a certain point where you start to lose the positional tolerances. So you really want to see where your pressure values from DOE were. And with thicker layups, you really want to consider doing the offset of the layup surface after every 2 or 4 millimeter to be able to compensate correctly for that thickness. Otherwise, the pressure can start to really get the positional tolerance messed up. Uh, yeah. So, assuming now we have run the layup, and now we'll definitely come across certain of the some of these issues. So let's talk about it. Uh, so the overheating will happen because the motion systems have to get to some velocity, they have certain acceleration, and it's during this acceleration period is where there is like either a burst of energy or there is like a lack, and then there's no bonding. So you would have more energy usually, and then you would end up burning this bit. So you really want to have cooled, water cooled and air cooled. With the fpxs, what we usually go for is what we call double layer air cooling. It works quite well consistently, but if you're running, I don't know, like with some more exposure to the heat, you might need to do water cooling. Yeah. The second bit is warping, and it's not a new thing, but it's if I think this is kind of a joke now in the office. It's almost impossible to do a flat layup with thermoplastic, and I think people should stop trying to do that. But because we have all of our test samples designed in flat, and with thermoplastic, it becomes a huge challenge. So yeah, I think this is something you just have to accept, that the first layer, or sorry, the just the layup, with even with the in situ consolidation settings, if you're running the layup, you will get warping. And just to release this thermal stresses, you would want to run it through the secondary process of relieving the stresses through or in an oven or autoclave, or whatever you have at your disposal. And that is the only, I think, way to get rid of them. Unless you're doing closed geometries where there is a possibility to get better results, but still there could be some internal stresses that you would want to relieve. I think, and the least discussed area is the fumes and the emission that come when you're running the system. As you're overexposing to heat and things like that, there is a possibility that you would end up burning at some places. There definitely are some areas where the tapes, how to say, sections of tapes bits fall onto the heating unit or in front of the heating unit and create these fumes. So you definitely want to have one of the air filters set up in your facilities. Hopefully that is helpful, but it's always good idea to get the yeah, get a filter system and then maybe run it from outside if possible. But I think with our system, we have like the home 3 system, it's possible to run being very close to it. So we just make sure that there's air filtration system running with us, and quite good. Yeah. So assuming we understood everything up to this point, that is starting, I understand it needs to be heated. I understand how to go about doing the design of experiment. I ran the layup, and I understand there are the common issues that I'll come across. Um, what is gonna get me the world class layup or thermoplastic part that I can create? And so these are basically nuggets that I would say you just have to understand that this is just the way it is. So the key factor is crystallinity that you want to achieve very good, and minimize the voids. And you can do that by going into having a very good heating and cooling control, um, having a very good pressure control, and uh, combining all these key parameter gets you there. There is no short key. So the key thing that you really want to um, optimize for is the crystallinity, and then the bonding definitely. So and you get that by really getting your design of experiment well run for your material. Definitely have to make sure you're not running a bad material. I have run dry materials which have less matrix to be actually melted. So that there is definitely, you are making sure that the input material is good for this process, and then it is not overheated, and it is cooled, and it's not running too fast. This is kind of one of the myths, that people want to run thermoplastic processes fast, and I've had like talks to a lot of experts, and what I've understood that there is only a certain speed at which you get diffusions. You can't hasten that process by just going faster, melting more. You're just going to degrade the plastic even more. So you would want to definitely not go really fast. So yeah, and you're trying to combine all these factors, and you can definitely have a secondary process to make sure that you can run your preliminary process of kind of creating a close to accurate preform available with you. But then you can also get in situ consolidated laminate. It is very challenging. So yeah, and I think of from this whole presentation, if you have to take something home, I would say focus on these four parameters, that is heating, uh, and with the speed combo is definitely the pressure and the bed temperature. So if you go and optimize for heating and speed, and pressure and bed temperature, I think with this combo you can achieve close to the best laminates possible with the given material set. Yeah. And yeah, I think that is what I would say. For one more thing, like what that DOE will enable, and as you run the full layup, that would enable is to for you to see is the how consistently you can run the process. So having trackability to what you're running, so pointed sensors, and you're calibrating, and you knowing all that data is very critical. So keeping track and updating yourself, if it is need to be changed in the program, cleaning the heating, because if the heat source getting exposed to some sort of dust and not giving out, you need to definitely make sure that you are maintaining. So if in order to make sure that you're running this consistently well, you just have to keep an eye open. So you can definitely run the systems like quite unattended, but then just need have frequent maintenance to be able to adjust for this parameter, and more digital twin style data capture possibilities that you can incorporate, the better. Yeah, but I think that that should cover the most most of the information that we wanted to cover in this webinar. Do we have some question, James?
We we did get a question. What would be an appropriate method to quantify degree of consolidation of the manufactured preforms based on our experience? Um, and so, yeah, so if I am understanding this correctly, you're basically asking, how would you confirm consolidation was good enough? And Pravin ran some pretty extensive testing for an entire week once last month. So I'm sure he would have some input on that.
Yeah, I think so. That is definitely, if possible, you want to do the the peel test and get the actual value. But when you're on the shop floor and running the system, you want like from your DOE. This is the point when you actually would know if you're getting good bonding is during your design of experiment, and you would take out the substrate tape and the incoming tape that you just placed, and then you would try to peel them apart. And the this is very simple and maybe not the best test, but that's how you would know like how well these tapes are bonded. The other method that I found that is, I think, is like very well known, is kind of a coin test style. So if you do run like 10 layers just in the DOE, and now you got this strip that is quite thick. Now if you try to make and you see if you're getting a metallic sound, it's generally a very good sign that you have achieved very good consolidation in these layers. But other than the standard test methods that are out there that you can usually run the extensive testing, which you need the test labs for, would be the peel test to actually figure it out. And then you can definitely do the cross section analysis with all sorts of, I think, the composites testing methods that are for thermosets similarly can be applied for thermoplastics. Yeah.
Yeah, and to add on to that, one of our customers recently published a paper, and their main criteria or main experiment was the interlaminate shear strength testing, which they had specific equipment for. And so that's probably the most scientific way to confirm you've been consolidated correctly. But yeah, if you're just on the shop floor running your quick experiments, the peel test or the coin test will give you a good indication of whether or not you have the right parameters to move on to the more scientific testing approach. We got another question. Roughly what temperature do you try to keep the compaction roller at? Does it make much difference as long as it doesn't burn?
No, it really matters because you're trying to kind of achieve controlled cooling with that. So, depending on the material, you would want to run it at high temperatures for high temp material, and at slightly lower temperature for low temp material. So you don't want to suddenly cool the material. It's not good. So you want to keep the warmth, but yeah, as you say, like you want to keep it towards the warmer side, but don't overheat it. Depending, as I said, so I think a good like approximation could be like close to TG. Yeah, and I think this roller is quite okay for that temperature. There is I think that's a good thumb rule to go with. But then you don't want to cool it down super fast. It's actually bad for your laminate. Yeah. Yeah, I think if that is all, James, I think we can wrap up. We really thank everyone to join on this webinar. We'll definitely make sure that we'll share the recordings from this webinar and the slides as well via an email. Yeah, to the email that you used for registration. So yeah, awesome. Thanks everyone. Bye bye.
Thanks everyone. Bye.